So by the end of this lesson, what I really want to get across to you is, number one, what does an ellipse look like? And number two, probably the most important thing is what is the equation, the general equation of an ellipse? But most importantly, how ellipses look very similar to circles. In fact, the shape of an ellipse looks like a stretched version of a circle, so we're going to talk about that. And the equation of a circle and the equation of an ellipse, even though they look kind of different at first, I'm going to show you by the end of this lesson that they actually are very, very closely related. So if you take the equation of a circle, you can kind of modify it to look like an equation of an ellipse because a circle is very closely related to an ellipse. So we're going to go through that logic. I want you to understand that the ellipse and the circle are cousins of one another and they're very closely related to one another. And as the problems and the lessons proceed, we will get into graphing ellipses more. We'll start shifting ellipses around in the XY plane. And so by the end of all of it, you'll understand where ellipses come from, how to derive the equation of an ellipse, and so forth. So the first thing I want to do, this is a long lesson. I have a lot to get out, okay? So I want to kind of get started. The first thing I want to do is draw the general shape of an ellipse. Now, I'm really not great at drawing ellipses. I'm sorry about that. They're almost always pancake shaped. So this is a terrible ellipse, I can tell. This is too fat, this is too skinny. It's okay though, because the accuracy doesn't matter so much for what I'm trying to get across. But you need to use your imagination and pretend that this is an ellipse, which is a stretched version of a circle. All right, now the thing you have to get used to with an ellipse is there are two special points inside of an ellipse. They're called focus number 1 and focus number 2. If you think about a circle, there's a special point to a circle also. It's just called the center of the circle. It's right in the middle, and there's only one of those special points. We call it the center. But for an ellipse, there's not just one special point. Because it's stretched out, there's two special points, and we don't call them the center because they're not in the center. We call them focus number 1 and focus number 2. So this would be the center of the ellipse, but the focus number 1 is somewhere over here. So I'm going to go ahead and put F number 1 right here. And focus number 2 is somewhere over here, F sub 2. There's two different focuses. We actually call them foci when you have two of them. Plural of focuses is foci. Now, as the one thing we're going to talk about mathematically is if you take an ellipse like this with focus number 1 and focus number 2, if I were to start to cram this ellipse together and make it less and less elliptical by cramming it together, eventually it would become a circle. And when it becomes a circle, focus 1 and focus 2 become right on top of each other, right in the center. So that's why a circle is a special case of an ellipse where both of the focuses kind of line up right on top of each other. And we're going to talk about that more. We're going to show the equations of why that's the case. But what I want to do now is I want to talk about the definition of an ellipse. What does an ellipse mean? Why does it have this special shape? All right, so the black curve is what we call an ellipse. There are points all along this curve, and those points I can label them anything I want, but I'm going to call this point P, and this P has an X and a Y coordinate because you have to imagine this ellipse in an XY plane with X coordinate and a Y coordinate, and every point on this black curve has an X and a Y coordinate. I could plot all those points and I would plot my ellipse. But what I want to get across to you now is what is the geometric definition of an ellipse, right? If you think back to a circle, it's easy enough I don't even have to draw it. A circle is a shape where the center is in the middle and all of the points on the circle are in equal distance all the way around from the central point. So the definition of a circle might be something like the set of all points an equal distance from the center. That is what a circle is. Well, an ellipse has a very similar definition. But because there's two special points instead of one center, the definition's a little bit more complicated. So I'm going to draw a distance from this focus to this point, and then I'm going to draw a distance from this focus to the same point. And what the definition of an ellipse says is that the black curve is the set of all points where if I take this distance to the black curve and this distance from the black curve to the second focus and I add them together, then the ellipse has a constant. Basically that total distance when you add them all together is a constant for any point on the black curve. So a better way to probably talk about it would be to write it down. What I'm saying is, much like a circle is defined in terms of the distance from the center. That's what all the points on the circle are. All of the points on the black curve are defined as like this. The distance from focus number 1 to the point P, the single point P right here, plus the distance from focus number 2 to the same point P has to be equal a constant. Now this constant is going to determine the shape and the size of the ellipse. So if I say that this distance plus this distance has to be 5, let's say, let's make it 5, then what it means is that this distance plus this distance must equal 5. Then it also means if I go to a point over nearby, then the distance between here and this point on the black curve plus this point down here must also be 5. The distance from this focus to this point on the curve here plus this distance here must be 5. You see the pattern? The distance down here to this point plus this point, this distance must be 5. This plus this must be 5. This plus this must be 5. This plus this must be 5. So much like a circle is a simpler version of that, the definition of a circle is the distance from a central point. This is similar. It's just because we have two special points, it's the sum of those distances must be a number constant. I'm picking the number 5 here, but just like the radius of a circle changes the shape of the circle, the sum of these, what we call focal radii, this is a focal radius number 1, focal radius number 2, has to be some number. And the different number we choose, just like the radius of a circle, is going to determine how big or small, how the thing looks in general. All right? So we're going to do a lot more with that in a little bit. We're going to actually derive in the next lesson the equation of an ellipse just from this definition right here. But I want you to kind of put that in the back of your mind right now and just remember that's what the geometric definition of an ellipse is. And what I want to do now is turn our attention back to the equation of a circle, because I want to focus this lesson mostly on how a circle, if you stretch it a little bit, becomes an ellipse. And the equation of a circle can be shown to look like the equation of an ellipse. So we've already done circles. Let's go and transform them and make them into ellipses. Now, for those of you who don't like surprises, I want to show you kind of the punchline before we kind of go too far here. This is the general shape of an ellipse. So the punchline, we're going to talk about this in great detail during this lesson and the next lesson, but I have a summary on the board here. I don't usually like throwing summaries at you, but I want you to have the big picture in your mind. Basically, this is an ellipse that's oriented horizontally, but you can also have the ellipse oriented vertically. So this is oriented where the long side is along the x-axis, and this one's oriented up and down where the ellipse is oriented on the y-axis. For now, just forget about this and let's talk about this one up here. All this is saying is that for an ellipse that's centered at 0, 0, that means it's centered on the origin, and the focus is, let's just pretend it's at some number negative c and positive c. We're going to talk a whole lot more about focuses later. Don't worry about sum of focal radii. We'll talk about that in the next lesson. But for an equation horizontally oriented like this, this is what the equation of the ellipse looks like. All right, so you have x squared, you have a y squared. Now stop right there and just remember back, the equation of a circle also has an x squared plus a y squared. Right? We're going to show that in just a second. But this one looks different because you're dividing by a squared, you're dividing by b squared. So basically, whatever is underneath the x squared term is the place where it crosses the x-axis. So if you write it as a squared, and then it crosses at the number a. In other words, if this were x squared over 3 squared, the ellipse would cross over here. And then of y squared over b squared, whatever number is down here determines where it crosses on the y-axis. So you can look at the equation and figure out exactly where the ellipse crosses on the x and the y-axis just by looking at it. You just take the square root down here, the square root down here, and then that's where they cross. The focus, we'll talk about how to calculate that, comes from this equation. We'll talk about that part of it a little bit later. Now, if you rotate the ellipse so that it's vertically oriented, you have the same thing. You have a focus at negative c and positive c. The focus always goes along the long direction of the ellipse, and you have the same kind of equation. X squared over something squared, y squared over something squared is 1. All I'm saying here is that the number underneath the x variable is where it crosses on the x-axis. The number under the y variable, you just take the square root of it, and that's where it crosses on the y-axis. And we have a long axis we call a major axis, and we have a short axis called a minor axis. So basically, we haven't gotten into problems yet, but the bottom line is when you write the equation of an ellipse down, it's going to be really easy to graph them. Because all you have to do is look at these numbers that are under here, and that's going to tell you exactly where the ellipse is going to cross. And then we'll want to sketch the curve of it. So don't forget your geometric definition. How this shape comes about is that this kind of focal radius plus this focal radius has to equal a constant. When we go through the math that we will go through the next section, we're going to pop out with the equations that we just talked about there. Now, what I want to do for the rest of the lesson is I want to show you that the equation of a circle as a starting point can be shown to look like the equation of an ellipse and how they're very similarly related. We're also going to get some practice with graphing. So what do I want to do next? I want to kind of put a little divider line right under here, because we're going to start kind of a new little topic. We're going to talk about the equation of a circle. So let's say we have a circle, right? We've done circles before. So let's take the equation of a circle. X squared plus y squared is equal to 3 squared. Now this is an equation of a circle. Notice what it looks like. X squared plus y squared is some number squared. It doesn't really look like the equation of an ellipse because there's a 1 over here, so that's different. Plus there's these things you're dividing by. These are all different, but you do have an x squared and a y squared in both cases. All right? So, and you do have a plus sign. Notice there's a plus sign here, and there's a plus sign here. So what I want to show you is that this can be shown to look like the equation of an ellipse, which I just wrote down over there, by the following thing. Let's divide both sides by what is on the right-hand side. So if I do that, I'm going to have x squared plus y squared. I'll divide the entire left side by what I have on the right, 3 squared. I know you know that that's 9, but let's go with it. And on the right-hand side, you have 3 squared over 3 squared. And by the way, what does this equation look like? What does this circle look like? We've done this so many times, I almost forgot to graph it. But basically, if this is an xy graph, the right-hand side is the radius squared. So basically what you do is you say what you have is, this is x squared plus y squared. On the right is going to be equal to 9, which is 3 squared. So basically the radius is squared on the right-hand side. So you have 1, 2, 3, 1, 2, 3, 1, 2, here's negative 3, and then 1, 2, here's negative 3 here. And you should all know, because we've done this so many times, that the equation of this circle looks something like this. It's not a perfect circle, but you get the idea. Basically, it's a circle centered at the origin because there's no shifting inside of these x and y variables there. And the radius is just whatever's on the right-hand side, square root of it, which is square root of 9, which is 3. So it crosses, notice, at 3 distance units away, all the way around. That's what the thing looks like. So it's very symmetrical, all right? So keep that in the back of your mind. Now, if we take this circle, divide by 3 squared, divide by 3 squared, on the left-hand side, when you have this guy, you can write this as x squared over 3 squared plus y squared over 3 squared is equal to 1. Y equal to 1, because 3 squared over 3 squared is just the number 1. And so when I have this here, I can break it apart. It's like, if you think about this as a common denominator, I could add these back together. The common denominator would just be the 3 squared. The top would be this numerator plus this one. So getting a little bit closer here, notice what this looks like. Okay, I can leave it like this, but I can also write it, if I want to, as x squared over 9 plus y squared over 9 is equal to 1. So notice that this equation of a circle, which looks very different than an ellipse, actually can be shown to have the exact same form of an ellipse. It's x squared over a number plus y squared over a number equals 1. And that's exactly what I told you it would look like. X squared over a number plus y squared over a number equals 1. So all ellipses, all circles I should say, can be shown to have the same form of an equation as the ellipse. The only difference is, notice this thing is oblong, it's stretched in one direction. Whatever the number a is, if it's like a really big number, it's going to stretch that ellipse out really far because a is where it crosses here. If b is really small, you're going to have a really thin ellipse. But if this number under y happens to be bigger, then it's going to stretch it in the y direction. If the number under the x is small, it's going to shrink it in the x direction. So the a and the b numbers in the equation of an ellipse determine how the thing is stretched, right? But if those a and b numbers in this equation are the same, then that means they're not stretched any different. They're stretched the same in both the x and the y direction. So if these numbers end up being the same, what you end up with is a circle. And we show that because the equation of a circle, when you divide through it, has the exact form as the equation of an ellipse with the same numbers on the bottom. So this is where it crosses in the x direction at 3 distance units away. This is where it crosses in the y direction at 3 distance units away. So get that in your mind, that the equation of an ellipse and the equation of a circle are basically the same. It's just that in an ellipse, those denominators and those fractions are different numbers. So what I would like to do now is, now that you know that the equation of a circle can be made to look like this, let's start playing around with it. Let's stretch this circle in the x direction. Let's leave the y direction alone. Let's leave it at 3 distance units away, but let's stretch it in the x direction. So what I mean by that is, let's go and draw another circle, another ellipse over here. And basically it's going to be a stretched version of the one that we have here. The one that we had here crossed 3 distance units in the y direction. But I'm saying let's cross and stretch it out 5 units in the x direction and 5 distance units in that direction as well. So you all know that this is 3, this is -3, this is 5, -5. So what I want to do is draw an ellipse that it's stretched exactly the same as that circle is in the y direction. However, in the x direction, it's stretched out. Whoops, messed that one up. Like that, something like that. I know it looks like a football, doesn't really quite look right, but you see what I'm saying? I'm basically stretching it out like this. What would the equation of that ellipse look like? What I'm saying is, the equation of the ellipse is basically the numbers in the denominator of the x squared term is how much it stretches in the x direction. The denominator term for the y determines where it crosses in the y direction. For a circle, these numbers are the same, so it's a circular shape. But if we stretch it 5 distance units out and keep this at 3 distance units, what would that equation look like? Right? Because this one was x squared over 9, y squared over 9 is equal to 1. Well, for the y squared term, it would be the same. Y squared over 3 squared, and you're going to have the equal 1. Why? Because we know it crosses at 3 and -3. But for the x squared term, it doesn't cross at 3, it crosses at plus minus 5. So this has to be 5 squared. So this, without any proof, I haven't proved it to you. I haven't made a table of values. I'm just saying we know how to graph circles. We know the equation of a circle can be shown to be the same as the equation of an ellipse. And by changing these denominators, it just changes where things cross. That's it. So this crosses at plus minus 5, this crosses at plus minus 3. We took the same circle, we stretched it out. Okay? Which means that this equation really is x squared over 25 plus y squared over 9 is equal to 1. Compare that to this one. This is x squared over 9, y squared over 9 equal 1. This is x squared over 25, y squared over 9 is equal to 1. Everything from here on was the same in the equation. We just changed this, and that's why it stretched it out. Now notice that this circle has a special point in the center, which we call the center. But ellipses have focuses, right? Which are, because we stretch it, we kind of take the center points and move them out. So I'm not going to calculate where the focus number 1 and number 2 is in this guy here. But the focus is going to be somewhere around here and somewhere around, let's see here, somewhere around here. I mean, I don't know, it could be a little bit closer, a little bit farther away. As we do more problems, we're going to calculate exactly where the focus is. I'm not trying to calculate that now. I'm just trying to show you that when you stretch a circle out, the special point, which is called the center, it splits into 2 focuses, one on the left and one on the right. Now, we talked about this a minute ago. The long side of the ellipse is called the major axis. The short side of the ellipse is called the minor axis. So if you're ever asked on a test which axis is the major axis or whatever, the x-axis, in this case, is the major axis. And the y-axis is the minor axis. Right? Because the major axis is basically, we're stretched in the x direction longer. In the y direction, we're not stretched as much, so it's the smaller one. It's called the minor axis. Okay? One more thing I want to kind of talk to you about before I go on is that you can kind of think of ellipses. You know, when you have a circle, you only have one radius from the center point. But for an ellipse, you can kind of think of each of these distances being different radiuses, different radii. So you almost have like 2 radius, a radius from this focus and a radius from this focus, okay? So you can kind of think of these numbers underneath as being the radius in the x direction and the radius in the y direction. For the circle, it's the same radius. But for an ellipse, the radius in the x direction is 5, and the radius in the y direction is 3. And that's just another way of thinking about it. Circles happen to be a perfectly round, symmetrical version of an ellipse. So that's why we don't talk about radius 1, radius 2 for a circle. But for ellipses, we do because of that. let me make sure I'm caught up here. The foci, the focuses, are always on the long direction of the ellipse. They're never on the short side. They're always on the long direction. We have a major axis. We have a minor axis. And the takeaway here is that an ellipse can be thought of as a stretched circle that has kind of two radiuses. One radii in the x direction, a different radii kind of in the y direction. Now, what we did already is we took this circle, we stretched it in the x direction, and we arrived at this. Now what I want to do is take this circle and now stretch it in the other direction. I want to leave this alone. I want it to cross at plus or minus 3 along the x direction, but I want to stretch it in the y direction. And then we're going to take a look at what the equation looks like in that case. So let's go ahead and draw an axis so we're all on the same page and we understand what we're doing. So what we're saying is we want to keep the original radius in the x direction being at plus or minus 3. But in the y direction, let's go up to, let's make it big. 1, 2, 3, 4, 5, 6, 7. So this is positive 7. 1, 2, 3, 4, 5, 6, 7. This is negative 7. Something like this. And so then if this is an ellipse that crosses at 7 here, and then goes down and crosses at 3, and then it goes down here and crosses at 7, crosses up 3, and then crosses up at 7. You see what I mean? It's almost like there's two different radiuses here, one in the x direction, one in the y direction. The radius in the x direction is 3, the radius in the y direction is 7, right? So then it's very easy to write down the equation of the ellipse, because all you do is you say it's got to be x squared over something. So you look at how far is it stretched in the x direction, where does it cross? It has to be over 3 squared. The crossing point on the y-axis is basically what is its radius in the, kind of in the y direction, which is 7 squared. And you just set it equal to 1. All right, so when you do the squaring, what you get is x squared over 9 plus y squared over 49 is equal to 1. And this would be the equation of this ellipse. It's centered at the origin because there's no shifting in the x and y direction. Only the numbers in the bottom determine how the thing is stretched out. And you can compare it to the equation of a circle. When we did all this math and we got down to this point, this is how much we're stretching sort of the radius in the x direction. This is sort of the radius in the y direction. So we kept the x direction exactly the same in this case. We only stretched the y direction, and that's why it stretches up like this. And then you can say that the y direction is called, in this case, the major axis. And this is the minor axis. And by the way, I mentioned this in a previous lesson, but one of the coolest things about ellipses is all of the orbits of the planets in our solar system, you know, not just planets, but satellites, moons, anything orbiting our sun that's on a trajectory that's not an escape trajectory, just going around and around, they're always elliptical. And what is special about these focuses, these foci, is that, for instance, if this were the orbit of Pluto, let's say, the sun would be at one of the focuses, one of the foci of that ellipse. So all of the planets going around the sun are going in elliptical orbits with the sun being at the point we call focus number 1. Focus number 2, way out in space, doesn't have any meaning really. It's just empty. But the focus, the thing you're orbiting, is actually at one of the foci of the ellipse that you have. Okay, so let me make sure I've got everything straight. We started with a circle. We showed that it really can be shown to look like an equation of ellipse. We stretch in the x direction, and that means that we have the number getting bigger down below the x squared term. So that stretches in the x direction. When we have the number getting bigger in the y direction, that we show that the thing is stretched in the y direction. And now what I want to do is talk a little bit more about these focuses, because I didn't draw it here, but here, somewhere around here will be a focus, and somewhere around here will be a focus. It always lies along the long end of the ellipse somewhere. There's a focus 1 and a focus 2. Now what I would like to do is talk a little bit more concretely about why an ellipse, if you start to squish it down into a circular shape, really does become the equation of a circle. We've kind of shown that here, but I want to do one more little kind of thought experiment with you to make sure we're all on the same page, because it's kind of cool. All right, so let's think of a really long, skinny ellipse, something really, really long and skinny. If it's really, really long and skinny, then the number that appears under the x direction has to be really, really big, because that means it's going to cross really far away. The number under y, when you take the square root of it, that's where it's going to cross in the y direction. So if I want a really, really skinny ellipse, let's do that. Let's draw a long and skinny ellipse. Let's say I have an ellipse that looks something like this. It goes way out here, crosses way out here, something like this. That's not perfect at all. But let's say it crosses over here at -10 and +10. And let's say it crosses at -3 and +3. So it's really long and stretched out. What would the equation of that ellipse look like? Well, it follows the same form. It's centered at 0, 0, so it's x squared divided by whatever the crossing point is squared, right? And then plus y squared divided by wherever the y crossing point is squared is equal to 1. This is exactly what I have written on this board here, that whatever here is labeled as a squared, but the crossing point is not a squared. It's basically the square root of that. So whatever's on the bottom, you take the square root of it, and that is where it crosses. Same for the y value. So here, take the square root of this, I get 10. Take the square root of this, I get 3. And that's how I know that that's the equation of this ellipse. So another way to write that would be x squared over 100 plus y squared over 9 is equal to 1. This is the equation of this ellipse. Now somewhere along the long direction is a focus number 1 and a focus number 2. So let's put it here. I don't know exactly where they are because we haven't calculated it. But here's a focus, we'll call it F1. And here's a focus, we call it F2. Now what I would like to explain or explore with you is that as we squish this ellipse and get it more and more circular, of course the boundary will get more circular, but these focuses will get closer and closer together as well. And eventually we're going to get to a circle. And when we get to that point, then the equation of this ellipse should look like an equation of a circle. And we're going to show that right now. So let's do that. Let's draw another one of these guys. Let's make a slightly less elongated version of this. So here I want to cross at, let's say, 6 and -6. Probably not symmetrical, so let's do something like this. -6, something like this. And let's go ahead and leave it at ±3. Now, all I'm doing, I'm keeping this the same, but I'm showing you that we're basically making this thing slightly more circular, like this. Now, somewhere in here is going to be a focus. So let's call it right here and right here. Call this F1, F2. But notice as we squished it, this focus has gotten closer. Now they're closer together. I'm not putting the actual numbers here, but you know that they have to move closer together. What would be the equation of this ellipse? Well, it would be x squared over wherever it crosses squared. So 6 squared is 36. Y squared, take the crossing point and square it, which is 9 is equal to 1. So this is the equation of this ellipse. So notice that this is 109, so you can tell it's really, really stretched. This is 36 and 9. It's not quite as stretched, but it's still pretty darn stretched. Now let's do another one, and let's keep these guys, let's make them a little bit closer together. Let's make this over here now at 4 and -4, and then this will be at 3, and this will be at -3. So this is going to be even more circular. This is not a good ellipse. I'm sorry about that. It's actually a really terrible lumpy ellipse, but you can see it's getting more and more circular. And then, of course, as we squish it closer together, the focus must be getting closer and closer together. And so what's the equation of this ellipse? X squared over the crossing point in the x direction squared, 4 squared is 16, plus y squared divided by the 3 squared, which is 9, is equal to 1. So you see what's happening as I squish it closer and closer, these numbers are getting closer and closer to one another. So now what I'd like to do is I would like to get it really, really, really close to being a circle. Really, really, really close to being circular. So let's take it like this. This is x, this is y, and let's say this is 3, this is -3. Now, this would be 3. Let me go ahead and mark a 3 right under it here. Here's a 3 right here. So this is supposed to be a circle. But what I'm going to do is I'm going to make it a little bit, just a tiny bit oblong. So it's going to cross at 3, but it's not going to cross at 3 here. It's going to go just beyond it. Going to cross at 3 here. It's going to cross just beyond it. So it's very slightly egg-shaped. And I probably should have drew it even closer in. It looks a little bit like the one above. But you see, if it were a circle, it would cross everywhere at 3. Here I'm crossing very slightly out. And because of that, the focuses now are really, really close to being on top of one another. What's the equation of this ellipse? X squared over, let's just say for giggles, that this crosses at 3.1. So I'll have to square the 3.1. The y squared will be 3 and positive negative 3, so it'll be 3 squared. So what do I get for an equation here? X squared, what is 3.1 squared? I get 9.61 plus y squared over 9 is equal to 1. So you see when the ellipse gets really, really close to circular, the bottom numbers are becoming basically equal. Eventually I'm going to get to the point where they become the same. So let's do that right below here. And so here is 3, here is 3, here is negative 3, here is negative 3. And it's not going to be perfect, but I'm going to try to draw a circle here. It's a lumpy circle. I know it's not perfect. But what's this equation look like? Well, it's going to look like x squared over 3 squared. I don't want to write this. 3 squared, which will be 9, plus y squared over 3 squared equal 9 equal to 1. Now this is the equation of the quote-unquote ellipse, but now notice what's happened is that focus number 1 and focus number 2 are so close to one another, they're essentially right on top of each other, right at the center. So both of the focuses kind of get closer to one another. This is the equation of the ellipse here. Now what do you think is going to happen if I multiply this equation by 9? If I take this equation, let me kind of space this out here, and multiply by 9, sorry I'm running out of space here, multiply by 9 here, what am I going to get? I'm going to distribute the 9 into both of these. The 9 is going to cancel with this. The 9 as it distributes in will cancel with this one as well. So basically the 9s are going to disappear from the left. So what you're going to have is just x squared plus y squared is equal to 9, which is the equation of a circle. Because what this is x squared plus y squared is equal to the radius squared. It's a radius of 3. And that is the main idea of what I'm trying to get across to you in this lesson, is that I can start with a really stretched ellipse with 2 really far away foci, right? I can write the equation of ellipse. These numbers are really different because it's stretched really far in one direction. But as I bring them closer and closer, the numbers, because the crossing points are getting closer, the numbers are getting closer and closer until finally I'm just on the other side of 3 and they're really close together. But if I ever make them exactly equal to one another, then it becomes, even though you can write it as the equation of an ellipse, you can write it and multiply through and get it to look like what we think of as the equation of a circle, with both foci lining up on top of one another. That's the most important thing to come up with. So we started the lesson by talking about the definition of the ellipse. And we talked about the fact that the distance from the focus to any point on the ellipse plus that distance to the other focus has to be a constant for every one of these points along the boundary. And then we showed that you can start with the equation of a circle, you can start stretching it, and then you end up with what we call the equation of the ellipse. Now what we're going to be doing as we solve future problems is we're going to use these diagrams a lot, but the bottom line is the crossing points for the ellipse are very easy because you read them right off. You have to take the square root, of course, down below here, but it's basically right there in the equation. And it's always going to be centered at 0, 0 unless you have some shifting going on, which we're going to get to much later. We're not moving the ellipses around yet. We're going to get there. So make sure you understand this. I encourage you, grab a sheet of paper, try to take some of these ellipses that I had here and graph them yourself. Make sure you understand what's going on and you understand the concept that the foci are getting closer and closer and closer together. Eventually, when you get to a circle, those two foci line up right on top of each other. And the equation of that ellipse in this case then becomes the equation of a circle. So now you see circles are just a special case of the general thing that we call an ellipse. Learn anything at mathandscience.com.